Hello, everyone. Thank you all for joining. Today, I am happy to introduce Dr. Eric Brubaker from Sandia National Laboratories, who's going to be presenting on aperture-based radiation imaging techniques. So, Dr. Brubaker, whenever you're ready.
All right. Thanks, Will. So thanks to you, Will, and the other organizers for the chance to be part of this. So I'm a physicist at Sandia National Labs. I work in the Radiation and Nuclear Detection Systems group at Sandia. I'm at the Livermore, California site. And so today's talk on aperture-based imaging techniques is kind of a counterpart or a partner to what Will presented the other day on double scatter imaging. So you'll see that this is kind of another class of radiation imaging techniques. So I'll go ahead and get started. The outline here, the general idea is I'll go through a little bit of introduction on applications, though there's not time to delve too much into that. And then talk at the sort of theoretical or conceptual level about aperture imaging, and then go into some specific systems and results, mostly drawn from my own research that I've been a part of in my time at Sandia. The pictures here are some examples of those aperture-based systems. Got coded aperture imager and a couple of different time-encoded imagers. And I'll include a couple of other results. One from a gamma coded aperture imager, just to kind of demonstrate the gamma side of things. Though my personal experience and research has been primarily focused on neutrons, fast neutrons, fission energy neutrons in particular. So that's the roadmap here. So like I said, just a brief kind of coming into this through the application side, because that's how we kind of think of the research we do is all towards towards some application in nuclear security. So we're looking at developing systems that could eventually be applied in a number of different kinds of scenarios, and there's two kind of broad classes that I've divided them to on this slide. There's applications where the goal is to detect a source, and applications where the goal is to image a source. And in both cases here, I'm going to be very upfront that we're focused on special nuclear material. So that's partly what drives the neutron focus. And there are other applications where other isotopes are of interest, but we're primarily interested in either detecting nuclear material that could be used to make a nuclear weapon or that's already in the form of a weapon. And so some of these applications are things like cargo screening at ports and border crossings, standoff detection. You might imagine like a search situation, an urban search, or searching a facility. And then on the other side, and those are applications where you've got primarily distinguished by a weak signal. If it's a strong signal, it's an easy problem and we don't need to develop fancy detectors to do it. The interesting cases or the hard cases where you have a weak source, either because it's far away or it's a small amount of material or it's heavily shielded. On the other side are the what I think of as the more imaging specific applications. And in this case, maybe we're just trying to understand everything we can about something, in the emergency response scenario, you have a radioactive source in a box and you want to learn everything you can about it to know how to respond, whether it's a threat and how to respond to that threat. And arms control treaty verification is an area of particular interest for me. And this is a situation where, one of the canonical kind of scenarios would be an item is presented in a treaty as a treaty accountable item, maybe as a warhead or as a component. And the goal of a measurement is to kind of verify that the item is as declared. And there's plenty of other interesting aspects of the treaty verification application, like not wanting to learn too much information about an object, but again, not time to go into too much detail other than that. So from those sort of application level flows, the way that I think about three different tasks that we might want to do with radiation, with directional detection systems. So imagers, kind of the feature of imagers that distinguishes them from other detectors is that they have directional information, but that directional information is not always the same across different systems. So the first of these potential tasks is, again, detection. This goes back to the previous slide where a couple of those scenarios were specifically focused on this question of whether there is or isn't a localized source present in an environment with respect to radiation background, which is always present at some level. And the distinguishing characteristic there that we can access with directional information is that background tends to be diffuse, maybe not completely uniform, but slowly varying spatially or with respect to angle. Whereas a threat source is much more likely to be a localized source, either a point source or something that at the distance, from the detector that it's at is effectively a point source. The second task is localization. So once you know that you have a source, where is it? And so again, directional information is obviously important here, but it's not the most general problem. You kind of in this middle section, we're assuming we have a source and we just need to determine where it is. So for example, which apartment is it in an apartment building that we're sitting outside of, or which cargo container in a stack of containers. The third category there is what I usually reserve kind of the word imaging for, which is this most general case where we don't know what's out there, and we want to generically reconstruct the distribution of emitting material. There could be multiple sources, there could be extended sources. We, in that case, need full image reconstruction methods, and we need detectors and imaging systems that have the best angular resolution in order to do this. Let's see, let's just go on. So, so in that context, I'm going to talk about aperture imaging. And so I'll first take a few minutes to tell you what I'm not going to talk about. So the way I think about imaging of energetic radiation is, let's start with what we usually think of when we talk about imaging, which is, taking a picture. We all have cameras that we carry around with us all the time. How do optical cameras work? What happens when we take a picture of the environment around us in optical photons? Well, there's some kind of lensing system which converts where a photon is being emitted in the scene in front of you into a corresponding position on some position-sensitive detector inside the camera. And so you get this nice one-to-one mapping of where you're detecting that photon on the position-sensitive detector to the real-world location. But the way that works is by bending the light inside the lens. And that can get very complicated, as you see here on this top picture, but effectively, the key thing that's going on is at the interfaces between the lens where there's a change in index of refraction, light gets bent, and so you can kind of steer it in the direction you want. Unfortunately, that doesn't work for energetic radiation like high energy photons, gammas, or X-rays, or high energy neutrons. So we need different approaches. And I think of those different approaches as falling into two categories. So on the left side of this slide are the kinematic imaging approaches, and that's really what was the focus of Will's presentation yesterday, I guess it was. So that's, in the case of neutrons, we might call it scatter cameras or double scatter imaging. In the case of gammas, we call it Compton imaging. That's where we use the kinematic information from the radiation interactions in the detector to unfold or to reconstruct information about where the particle came from. So I'm not going to talk any more about that. I'm going to talk about what's on the right side of the slide, or the aperture imaging techniques. So I'll start by just introducing pinhole cameras, which again is not specific to radiation. You may have built pinhole cameras in high school or something like that for optical light. And a sort of natural extension of pinhole cameras are coated apertures, where you have many holes in a mask. And then I'm going to talk about time encoded imaging, which, as you'll see, is a very kind of very closely related to coated aperture imaging, but in the time domain rather than the spatial domain. All right. So let's talk about pinhole imaging. How does this work? The basic concept, as you can kind of see in the top picture there, is that you have a there's an opaque mask, so that would be the front of the box here, and there's a small pinhole cut out in that otherwise opaque mask. What that means is that particles, or photons in the case of optical lights, stream from the scene that you're interested in through that pinhole onto a position-sensitive detector on the other side of the mask. And so, you know, just by inspection, you can see in pictures like this that what you end up with is an inverted image because the particles, you know, stream through and kind of cross each other through that pinhole. You end up with an inverted image of the scene on your image plane. So that's the simple kind of version of this, and it works just as well with gammas and neutrons as it does with optical photons, as long as you have an opaque material that you can cut a pinhole in and a position-sensitive detector that you can record the arrival of the particles on. So let's look at what the kind of parameters of interest are in a situation like this. So one is the pinhole size. And you can kind of see in this middle picture here an example of what happens as you start to increase the pinhole size. First of all, why would you want to increase the pinhole size? Well, because if you have, you know, truly just a negligibly sized pinhole, then a negligible number of particles or photons will stream through that aperture. And so the sensitivity is low. You need a long time to collect enough events or particles on the rear plane to reconstruct the scene. So there's some trade-off here. As you make the pinhole larger, you allow more particles through, and so you have higher sensitivity. You make an image more quickly. But as you can kind of see depicted here, you lose some resolution because the particles coming from a given point in the scene now impinge on a larger region of the spatially sensitive detector. So another parameter here is the distance between the mask and the detector. And you can see from the geometry that as you move the detector farther away from the mask, the rays diverge farther, and so you get a larger magnification. If you can instrument a large detector area, you'll get a magnified view of the scene. But then again, the trade-off there is that you have to make a larger detector if you want to catch all those rays. On the other hand, if you have a smaller detector, that will limit the field of view, limit the angular area of the scene that you have that you can record particles from. So there's a trade-off there as well between magnification and field of view. A couple of other things that come into play, especially for energetic radiation. When you're thinking about energetic gammas and neutrons, there's no, materials cannot be opaque with infinitely thin thickness, right? You need some thickness, especially thinking about high energy gammas or neutrons. You may need centimeters or inches of material. You'll see later that we typically use 2 to 4 inches of plastic for the neutron-coated aperture in order to attenuate those particles. So because of the thickness of the mask, and then similarly the thickness of the detector, because you also need a significant thickness of detector material in order to capture the particles with a high probability, that adds some extra issues with the imaging part. So you can kind of see from this picture here, there's a image plane resolution in general, compared to photographic film. Position sensitive detectors for neutrons and gammas tend to be have a different kind of resolution, and that's partly just due to the typical size of an element, let's say, but also due to the thickness. So you can see here for a source at the orange star location, as it streams through that mask, it's going to hit 1 pixel in this detector cartoon here, whereas the one at the yellow location streaming through the mask, because it's coming in at an angle, particles could be detected in any of the 3 bottom pixels in this cartoon. So that's a contribution to the image resolution, as well as just the size of each element, which may be limited by other factors. And then finally, the mask thickness itself causes an effect called vignetting, where you get different amounts of light or intensity of the particles through the mask as a function of where you are in the field of view. So you can see that if we went even farther up than this yellow star, at some point we get to a point where there are no kind of free streaming paths through the pinhole because of the thickness of the mask material. And so that's one way to think about it. Even for this yellow case, you can see that the beam that's fitting kind of unimpeded through the mask has a narrower angular size than the orange one. But as you go even farther, you might start clipping a corner of the mask, and so the opacity will not be complete. It's partially transparent, so you also have sort of a shape to that, to the transmission function of the mask. So I wanted to go through some of these issues in detail, because all of this applies no matter what kind of aperture method we're talking about. Okay, so all of these characteristics are things to keep in mind, and when we're designing a detector system, we need to decide where we want to be in all those different trade-off spaces. So now let's talk about taking the step from a pinhole camera to a coded aperture imager. And as I kind of alluded to earlier, the reason to do this is when we want more sensitivity than a small pinhole can give us, but also better resolution than a large pinhole can give us. So the top cartoon here is the same one as the previous page. Now, let's say we need more sensitivity because we want to make short measurements, and so we start increasing the size of the pinhole. Well, pretty soon we get to a situation like this where the information is not that useful. Both of these source positions are covering a large fraction of the detector pixels. They're not going to be that distinguishable. It'll be hard to kind of untangle everything going on. The information content is reduced by the size of that pinhole, even though it's true that we're getting more particles through. So what else could we do? Well, instead of making one large hole, we can make many smaller holes. And that's kind of the insight that leads to a coded aperture. The sensitivity is still increased because there are multiple holes, multiple apertures that the particles can go through. But the resolution can still be quite good, because the kind of level of distinguishability for the different particle source positions here is still high. The downside is that you have a much more complex situation and complex reconstruction, because you no longer have a one-to-one mapping like you do with the pinhole between the source location and the detected location. Instead, you have this kind of composite response that is going to require more complicated reconstruction to unfold. So that's one way to think about coded aperture imaging. Now I'll give you kind of a different picture of it that maybe will kind of intuitively help understand what's going on. So this is a picture of a one-dimensional coded aperture system. You have some position-sensitive detection plane here. Each of these blue boxes is a independent pixel. And then the mask plane up here is just think of it as a completely opaque material. So in the picture shown here, you have radiation coming in from one particular direction. as you can see here, is shown as a plane wave, and if you go far enough away from the detector, even a point source looks like a plane wave. So that's kind of a standard way to think about these things. Though you can also perform reconstructions that assume sources at different distances. But in this case, the plane wave comes through, and you can see that where it passes through apertures in the mask, it hits the detector and produces a large signal. So the histogram here corresponds to a relative rate in the different detectors of this detection plane. Where the plane wave is blocked by a mask element, you see fewer events. It may not be zero, depending on how opaque this thing is, or exactly what the angle is coming in. There's and the finite thickness, as we were talking about before. There are ways that you get non-zero counts in these things. But the general idea is that if you look at this, you can convince yourself that based on the pattern you see here, even if you didn't know where those particles were coming from, you would be able to correlate the rate here shown in the histogram to the known mask shape, or the known mask pattern, and figure out where the plane wave is coming from. Okay, imagine that that plane wave coming in from a different direction, and how the pattern would shift on the detection plane, and you'll kind of see that what happens is you get kind of a cyclically shifted pattern on the detection plane as a function of where the source is coming from. All right, so now I'm going to sort of introduce this concept of time-encoded imaging, and what you'll see is that it's a very similar concept to what we just saw for coded aperture, but now instead of that position-sensitive detector plane, we just have a single detector, this orange one here. And this detector, instead of because there's just one detector, there's no kind of spatial shadow pattern being cast by the mask. But what we're going to do is take this same mask plane and move it across in front of the detector, and then we'll look as a function of time at what the detector sees. And so as that mask moves in front of the detector, you again see the plane wave coming from the same direction as before. It's sometimes obscured by the mask and sometimes streaming through. And if you look as a function of time, the rate that the detector sees is exactly equivalent to this spatial shadow pattern in the spatial coded aperture situation. Okay, so there's this very close relationship between coded aperture and time encoded imaging. So the kind of summary of that is that in coded aperture, you have a spatial modulation of a particle flux that comes from putting a fixed mask in front of a position-sensitive image plane, as shown here. In time-encoded imaging, we have time modulation of a particle flux that comes from putting a moving mask in front of, one, or all you need is one, or a few time-sensitive detectors. So you're converting that modulation from the spatial domain to the time domain. And so some of the reasons that this might be a useful thing to do, time resolution in detectors is on the kind of time scales we're talking about, where you can move the mask in front, is pretty much free, whereas spatial resolution means often many detectors, complex detectors, high channel counts, and so on. There's a sort of slightly more subtle point that calibration of detector channels is hard when you're talking about many channels making up a position-sensitive image plane. You need the cross-calibration among the channels to be very good, whereas in the case of time-encoded imaging, you need the calibration of a given detector to be the same as itself over time, over the duration of a measurement, which is a much less stringent requirement. The trade-offs, of course, are that with a single detector, we have fewer particles that we're detecting, and so the sensitivity reduces. Or alternatively, if you make that detector larger, then the resolution is poor. So it's back to more like the pinhole case in terms of the sensitivity resolution trade-off, but you have the advantage of the potential of high resolutions at low for simple systems. Okay, So a couple words about image reconstruction and focusing on the coded aperture here. So we talked about coded aperture is just an extension of pinhole imaging where you start adding more holes. So how are you going to do that? And we already kind of talked about this in the one-dimensional case, but the simplest way to do that is just poke a bunch of holes. Let's say we have a checkerboard pattern. So instead of one aperture, we've got a whole bunch of apertures in the checkerboard here. Well, that doesn't work too great because now you're getting more particles, but you can see because this is a repeated pattern, there's a whole bunch of different source directions that as they stream through this checkerboard, it'll look exactly the same whether a source is coming from one angle or kind of the next angle over that corresponds to a shift of the pattern by 2 elements and so on. So that doesn't work too great. Really what you want is to code a unique pattern for each source direction. And so this, here's an example where if you were to stare at this long enough, you could convince yourself that now we're in 2 dimensions instead of 1, that if you imagine a shadow projected from this pattern onto a position-sensitive plane, that as a function of where the particles are coming from, you're going to see a different pattern every time. So that's good. That means that any source location in the field of view will present a different shadow pattern, and therefore you can reconstruct that. Now, even better than that is that the pattern for each source is not just different and unique, but it's also orthogonal. And that's actually what this particular mask pattern provides. This is called a modified uniformly redundant array, and there's particular math that goes into creating this pattern. The rank 19 there means that there's 19 by 19 elements, though in fact what's happening here is that pattern is repeated 4 times in a 2 by 2 pattern with slightly different middle rows and row and column in between those 2 by 2. And so the key feature that this mask pattern provides is orthogonality. And that's a key feature. What orthogonality means is that not only are the different mask patterns unique, but if you kind of multiply them together, orthogonal, just like vectors, each of the source positions, you can think of the pattern that it produces as a vector in a space. And what it's saying is that those vectors, that the patterns are orthogonal with respect to each other. If you multiply them together, you get 0. They're independent. Mathematically, linearly independent from each other. And what that means is that you can't just distinguish a point source here from a point source here from a point source here. In fact, you can reconstruct superpositions of sources. And that's key for imaging when you have multiple sources or extended sources. So in fact, the great feature of coded aperture imagers, as you'll see, is you're not just reconstructing a point source. That's not that hard. But you can reconstruct a more complicated scene and determine the shapes and sizes of extended sources and so on. So that's great. Now the other thing you can do is say, well, that's really hard. I'm just going to make a completely random mask pattern. And the reason that's the galaxy brain here is because, in fact, as long as you have a large enough space here, the totally random mask pattern kind of mathematically approaches the orthogonality condition. So it actually works really well to have random masks. And this is just an example that I pulled from some astronomy paper here. I should have said that the coded aperture technique was one of the earliest applications was in astronomy for looking at very distant objects with primarily, I believe, visual, optical wavelengths. So in some cases, we'll just use random mask patterns because that has all the conditions that we need. I do want to go back to this one though, because there's another feature that's very handy in the case of a spatial coded aperture, which is that if we rotate this mask by 90 degrees, it turns into its own anti-mask. So if I switch them back between them like this, you can kind of keep your eye on a particular region and see that if the original mask has an aperture, then the 90-degree rotated version has a mask, and vice versa. The only case where that's not true is this very central point. But other than that, it's true throughout. Now, why is that useful? The anti-mask provides a way to, if you have data both with the mask and its own inverse, the anti-mask, you can, as you'll see in a minute here, you can figure out the sort of background, the part of your detected flux that's not coming through the mask, that's not modulated by the mask, either because the mask isn't completely opaque, or because it's coming around the sides, or because you have instrumental just noise in your detectors, or whatever it is. And so using both the mask and the anti-mask means you can kind of unfold that component of the data. And this mask is nice because that 90-degree rotation means that we can have just the same mask that we rotate to take the two parts of data. All right, so a little more detail and math here on the image reconstruction. The idea is that, so we have this mask pattern, and we can represent that with a vector or a matrix A. We're going to acquire data where the data is going to be a product of the source, the scene S, modulated by this detector pattern A. So that's kind of represented here by this operator. The A star S means the source distribution, the scene, has been modulated through that mask pattern A. But then there's also this background term, because like I said, you can have an imperfect opacity in the mask. You can have background, coming from other areas. You can have room return, scatter in the room, and so forth. So the reconstruction proceeds by decoding. This is the simplest version of coded aperture reconstructed. You decode that data with a matrix whose product with the original mask pattern is a delta function. And so if you kind of follow that through, if you multiply, or if you operate on the data D with this decoding matrix G, you end up with a delta function times S, which is what you want, but you also have this this background term now kind of propagated through the decoding matrix G. And so that's where, if you look down to the last bullet here, that's where I'm saying the anti-mask comes in. So if you have the anti-mask, then and you acquire an additional data set, call it D prime, with the anti-mask on the same source, distribution, but the background here, because the background is not modulated through the mask, it's the same B as you had for the original data set. And now you subtract those two data sets, you're subtracting off the background part. So the B's go away, and you end up with the difference between the source distribution modulated by the mask and the anti-mask. But because the mask and the anti-mask are opposite, the difference between those is the same as 2 times the original mask distribution. So obviously in real life, nothing ever works this perfectly, and you have imperfections in all of the steps here. But in principle, this is how you reconstruct an image using coded aperture. And here's an example with the detector that I'll introduce here in a second, of reconstructing a point source. This is the raw data that you see from the point source going through this mask, along with whatever background is there. And in this case, it looks like this is not done with the mask anti-mask, and though I'm not sure about that. And this is the image you reconstruct. So mainly seeing a point source there, but there is some point spread function. Nothing is perfect, and there's some blur to that reconstruction. Okay, so for the rest of the time here, I'm going to go through a few of the specific instruments that we've developed based on these concepts that we've been talking about for the last 20 minutes or whatever it was. And so I'll start with the Neutron Coded Aperture Imager. So this is a imager that was developed by Oak Ridge and Sandia in a collaborative effort. It was primarily targeted at arms control applications. And so what you see here is kind of the physical implementation of the concepts we've been talking about. Here's the mask part of this system. This is that same rank 19 MURA that I showed you in the previous slides. It's made out of high-density polyethylene because low Z materials are good at blocking fast neutrons. And it's fairly thick. Depending on exactly what we want to do, we can put different masks in here. They can be anywhere from 1 inch to 4 inches thick. And then the second main part of the detector here, back in the left side of the picture, is the position-sensitive neutron image plane. So we got a few more details on that in the next slide, but this ends up being 40 by 40 pixels of 1 centimeter each. So 40 by 40, 1600 total pixels. And you'll see that the image plane is smaller than the mask. That's often what you want to do, because in order to have a field of view where the multiple parts of the field of view are going to result in a fully coded mask pattern on the image plane has to be smaller than the mask itself. As we talked about, built into this system is the ability to rotate the mask. It's on a little rotating platform here, and so that it allows us to kind of, in an automated way, acquire both the mask and the anti-mask data. All of the separation here between the mask and the detector is adjustable. The mask thickness, as I said, we can change. We can put in different mask patterns with different size elements and so on. And so here's another example of just reconstructing two different sources. This is actually an emulated extended source. We took a point source, a Californium source, and moved it through a square pattern, and just acquired data kind of over time as it was moving through that pattern. So it kind of emulates what a square radiation source would look like. And clearly, there's spatial resolution on the scale of a centimeter or so that lets us distinguish shapes like that in this case, it looks like it's about 20 centimeters square from the point source. I want to point out that these slides that I have here are based on a presentation by Melinda Sweeney. So I want to credit her for most of these slides, this section here on the results from the coded aperture imager, and also our Oak Ridge collaborators, Paul Hauslawton and company. So just a little more detail on the detector system for those of you who are interested in neutron detection. This is each module here, each of these block detectors is 10 by 10 pixels, 1 centimeter each. So the total area here is 10 by 10 centimeters. Those pixels are 5 centimeters thick, and they're read out with anger logic by 4 PMTs. So the light that's generated by an event in one of these simulator pixels kind of bounces up through a light guide, spreads out to impinge on all 4 of those PMTs, but with a different amount, different ratios of how much light reaches the different PMTs depending on the pixels. And so you can kind of see a map here of, with the flood source, we see kind of 100 different hot spots. If we look at this plane of looking at the ratios of the different 4 PMTs, and so we can do a calibration and determine for then a given event that we see later, which pixel are we going to assign it to based on that. And this is just showing the pulse shape discrimination capability there, of course, which is very important for a neutron detector. All right, and then the final thing to say here is that we also added a thermal neutron capability by adding a screen of lithium-6 zinc sulfide scintillator here on kind of the far end of these plastic scintillator pixels. And so the light from that detector escapes, it goes through the scintillator pixels and arrives in the same way at the 4 PMTs. And because that scintillator is a very different thing. Its pulse shape is much longer. It's very easy to distinguish, as you can see here in the upper right plot, the thermal neutron events that happened in the lithium 6 zinc sulfide from the gammas and fast neutrons in the simulator. And the other element there is that we add a layer of borated polyethylene to the mask in order to block thermal neutrons coming through. And now all of a sudden we've got an imager that has sensitivity to both fast neutrons and thermal neutrons. In fact, it also has sensitivity to gammas, although the mask is not optimized for gammas, but gammas will be partially attenuated by that mask, and so we can also make gamma images at the same time. Though it's not optimized for that, as I said. So why are we interested in thermal neutrons? Well, thermal neutrons give you information on moderating material in the scene. So special nuclear material is always going to be emitting neutrons at fission energies, 1 to 5 MeV, let's say, is where most of them are coming. Some of those neutrons, if there's moderating material nearby, they'll downscatter. And what we end up imaging, if we're imaging thermal neutrons, is the surface of the last scatter where the thermal neutrons are coming from. So examples of what that gives us added sensitivity to are high explosives or shielding materials that might be nearby the SNM. So then I just have a few results to go through. And I'll just preface this by saying that this system, coded aperture imaging for fast neutrons with this detector is the best solution we have right now for fast neutron imaging at high resolutions. So if we're in that situation where we're close to a source, again, arms control, emergency response might be kind of typical applications there. This is the best system we have to get a high resolution image of the neutron emitting material. And high resolution in this context means, like I said, on the order of a centimeter resolution. Not certainly as good as you can get from an optical camera, but that's the scale we're talking about for energetic neutrons. So this set of results here is just showing the reconstructed images on the left fast neutrons and on the right thermal neutrons, where we have a californium source embedded in a polyethylene sphere. On the top row here is just regular polyethylene, and the bottom row is a borated polyethylene. So you can see that the borated shielding around the californium source means that not as many thermal neutrons escape. When the neutrons are downscattered, they will be more likely captured by the boron in the moderator. But in the top image here, we see the full size of the sphere if we image in thermal neutrons, but if we image in fast neutrons, we're seeing primarily the point source, the californium source that's emitting the neutrons. There's a little bit of, sometimes you could have a neutron scatter once in the moderating material and still look like a fast neutron at the detector, but primarily once it scatters, either it'll scatter down below the sensitivity range of the detector, or it'll thermalize, and then we'll see it in the thermal neutrons. So that's kind of the broad capability that we're talking about here. It's distinguishing between the fast and thermal images. Now there's a series of images that are looking at the Burke ball. And you guys may have seen the Burke ball before. It's a 3.8 centimeter radius sphere of weapons grade plutonium, 4.5 kilograms of weapons grade plutonium. There's a picture down here with where it's set up right in front of the imager. So this slide is just looking at a 12-minute measurement of the Burke ball bare, no other material around. And here I'm showing not only the reconstructed image on the right, but also the raw data on the left. This just gives you a sense for what kind of shadow pattern we're seeing for something that's not a point source, but has some extent. And then how that gets reconstructed, through the procedure that I talked about before into the image on the right. So again, for the fast neutrons, we see something, and in these images, generally you'll see a dotted line corresponding to the true measurements of things in the scene. And so we see a fast neutron signature coming from the whole Burke ball. We don't see much of a thermal neutron signature as expected because there's no nearby material to moderate neutrons. So what happens if we put an inch of polyethylene around the burp ball? This happened to be a long measurement or overnight measurement, and so we get very high quality images here. And you can see that again both in the raw data on the left and the reconstructed image on the right. Again, you see the fast neutrons, we see the smaller extent of the burp ball, whereas in the thermal neutron image, we see the larger size of the moderating polyethylene. And I'll go fairly quickly through the rest of these. They're all sort of variations on the same theme, but shorter measurements with lower statistics. In this case, we've got the burp ball, a 1-inch void, and then 2 inches of poly. And so again, for the fast neutrons, in all these cases, what we're looking for is that we see, in the fast neutrons, we see the SNM itself. We see where the plutonium is emitting. Whereas for the thermal neutron image, we see the whole moderator. Now, there's interesting questions about how you could analyze this quantitatively and sort of what do we expect to see, given that the moderator is thicker at certain location, certain kind of lines of sight than others. But qualitatively, we see what we expect here with the larger size for the thermal neutrons. Now, this is getting to the large end. We've got a burp ball, a 3-inch void, and then 3 inches of polyethylene. And again, the fast neutrons are fine. We're starting to lose statistics with thermal neutrons, and in particular, the larger the region that of an extended source, the harder it is to image everything. You can think of it as every point in that image is acting as background to every other point. So it becomes harder to reconstruct images with larger size or source distributions with larger size. And then finally, this is a case where the burp ball was sitting in just one hemisphere of polyethylene. So the polyethylene was not completely surrounding it. And again, you see the plutonium in the fast neutron image and kind of half of the area filled in the thermal neutron image. So just again showing that we're sensitive to that spatial distribution. Okay, so I want to quickly talk about gamma-coded aperture here. So this is, the idea is just to kind of say what's different if we're talking about gammas rather than neutrons. Well, you have different gamma ray production physics. You have different gamma interactions, the way the gammas interact with the mask and the detector. And typically, for when we're talking about plutonium, for example, you have higher rates of gamma emissions than neutrons. And so when you're designing a detector, you're going to be using different detector material, of course, something with better gamma sensitivity and ideally spectroscopy capabilities like germanium or CZT. Different mask materials because you want to have the best attenuation for those gammas. You can generally get away with smaller thicknesses on the detector and mask, especially for lower energy gammas. And finally, you can take advantage of the spectroscopy capabilities. So this is a couple results from the Oak Ridge. Klaus Ziak provided these images. So this is the Oak Ridge coded aperture imager for gammas based on high purity germanium. There's a double-sided strip detector inside here, and you can see the mask is, I forget right now, I believe it may be a tungsten mask. And so what we'll see here is this is a measurement where there were 3 sources present in a scene. And so we're seeing a camera view of the room with the reconstructed image overlaid on it, and you clearly see the 3 sources. This is the spectrum as measured by the high purity germanium, just kind of integrated across the whole image. And one of the fun things you can do with a gamma coded aperture imager like this is you can restrict to just one point in the reconstructed image and ask what's the spectrum, or vice versa, you can restrict just to one part of the spectrum and ask what's the reconstructed image. This is just showing the zoom capability. As I mentioned before, if you change the separation between the detector and the mask, you get a different zoom in the field of view. So that's what's happening here. It's a different measurement with a different separation. And now, if we kind of look at what's the reconstructed spectrum in one region, we see one source type versus looking at the other locations, we see a different spectrum corresponding to the other sources in the scene. I believe there's a barium, uranium-232, and cobalt. Is it cobalt-57 with those low energies, something like that? So that's another interesting thing, and you'll see that as you have different kind of requirements for the gammas, you end up with a different looking detector system, in this case quite a bit smaller. That makes it more portable. It also means that there are fewer artifacts due to the thickness of the mask and the thickness of the detector. And now in the time we have left, I want to talk about a couple of these time-encoded imaging systems. So we talked about time-encoded imaging just in the sort of one-dimensional context, but now this is looking at what happens if you take that to into the two-dimensional limit. So this detector system has the coded mask. Now in 2 dimensions, it's a cylindrical mask, so it's not coding source locations above and below the detector, but anything kind of in a band around the detector. Inside that cylindrical mask is just a single liquid scintillator cell, 1-inch diameter by 1-inch thick. And if we put a source out, a californium source at 2.5 meters, and we rotate this mask around, over time, we see different rates on that single pixel detector. And in fact, this rate plot here is as a function of angle. If you imagine rotating the mask many times over some period of time, you can stack on top of each other the different periods of time that correspond to single rotations. And so you can kind of build up this picture over 360 degrees. And if we use if we reconstruct from this picture here, from this rate plot, the only information that goes into this reconstruction is this plot here, as well as the known mask pattern. We could reconstruct a point source. So I'm always amazed when I look at this stuff that, kind of this what looks like a bunch of noise, though it's clearly, if you pay attention to the amount of time, that clearly these are much larger than statistical deviations. There's enough information in there to reconstruct this scene. So that's a point source. That's one thing. But what happens if we look at multiple sources or extended sources? So in this case, we've got 2 californium sources that are matched sources at about 2 meters from the detector, and we're moving them closer together to see how close they get before we cannot distinguish them anymore. And that's one measure of detector resolution. So you can see at 5 degree separation, we can tell them apart pretty easily. At 2 degree separation, even with the 24-hour measurement, they kind of blur into each other. So that's sort of the limit of resolution of this system. And this is all documented in this paper here. And finally, if we do another one of these extended sources, again, an emulated extended source where in fact we have a point source that we're moving through a pattern, a ring pattern, we can reconstruct these images. So again, fascinating to me that with a single detector and just looking at the rate over time, we have the information that's necessary to reconstruct an extended source like this. The downside, as you can see, is the length of time that takes, because we're talking about just a single one inch detector rather than a full plane of detector. It takes a lot longer to get the information. So that's just 2 different positions in the field of view for that ring source. Okay, so I think I've said those things, and I'll just finish up here with a couple of results from a different detector system. So this is a different kind of application of time-encoded imaging where we're talking about addressing the standoff detection problem or the weak source detection problem. So what we're looking for is a way to find a very weak signal. So this example of a plutonium, an IAEA significant quantity of weapons-grade plutonium at 100 meters from a detector, we're talking about a signal to background of like 1 to 50. And so that's a very weak source. If you just think about statistical considerations, if you have a counting detector, depending on the assumptions you make about the efficiency of that detector and its size, you can still detect a very weak source with respect to background. But that's only if you know exactly what the background is supposed to be. if you have a systematic uncertainty on that background rate such that the signal rate at the detector is within the uncertainty on the background, then no matter how long you count, you can never detect that there's a source there. All you can say is that the source, the rate you're detecting is consistent with the kind of prior knowledge of the background. But if you have directional information from an imager or from this TEI 1D system, then you can, one way to think about it is simultaneously measure the signal in the background because you're seeing the distinction between the slight enhancement at one particular direction relative to the diffuse background, and then you can detect that source. So I will go quickly through this because we're out of time. The detector system is 4 very large simulator cells, each read out. So these are 12-inch diameter by 15-inch simulator cells. The goal is just to have as large a sensitivity as possible. Each of them is read out by 4 PMTs, 4 5-inch PMTs, and they're kind of set up in this diamond pattern, and then this whole platform rotates. So now instead of a mask that's time encoding, you know, the particle flux, each detector is being obscured by the other detectors. So each detector is acting as a mask for the other detectors. And so what we see if we look at a particular source location and look at the rate pattern in each of these detectors, just focus on one of these curves, and you see that when the detector is rotated such that it's exposed to the source, you get a high rate, and as it rotates behind the other detectors, you get a lower rate. So again, for the detection problem, what we're looking for is evidence of this modulation pattern. If we have a uniform background, then as the detector rotates, it'll just be flat in all of the detectors. But if there's an enhancement coming from one direction, then we'll see that modulation pattern. And so this is a result of a test where we put a californium source out at 100 meters. This is a stronger source than what I mentioned in a couple slides ago. It's a 1 millicurie californium source. But as far as I know, this is the first demonstration of detecting a source using the neutron signature at a distance of 100 meters. And we were able, with this detector, to show that detection, which we defined as 90% true positives and 10% false positives. We were able to do that in 720 seconds. The pictures here are from real data at not the 100 meter, but a 40 meter standoff. So you see a fairly pronounced pattern in 1 hour. At 100 meters and only 720 seconds, the distributions are much more flat, but statistically, that's the conclusion, is that statistically we can see it at this level in 720 seconds. So that's also there's a paper documenting that result. And so I'm going to skip over this part, though it's kind of interesting. This is the use of an optical coated aperture to help determine a position of a radiation interaction in a larger detector. But if anybody has questions, I can go back to that. So I just wanted to conclude by saying that we talked about different system parameters, things like the size of an aperture or distance between the mask and detector that affect these trade-offs for these aperture imaging systems. And then that, from those concepts, we can get to a very wide range of different systems, from the spatial coded aperture to the 2-dimensional time encoded imager to the 1-dimensional time encoded imager that sit in very different places on all those trade-offs. So they're really targeted towards different applications if we go all the way back to the tasks and the applications that we started with. So I don't, I also work on double scatter imaging, and I also am interested in transmission imaging. So I would in no way say that these aperture techniques are better in some way, but together with double scatter imaging and transmission imaging, which we haven't talked about at all, these are part of a toolkit that we can pull different concepts out to image energetic radiation. And looks like Jack would like to contribute here too. So with that, I'll stop, and I apologize for going a little bit over time, but I'm happy to stick around as long as people have any questions. And thanks for your attention.
All right, thank you very much, Dr. Brubaker. If anyone has any questions, please feel free to enter them into the chat.
I see one here from earlier, why can't gammas be lensed? So if you think about how gammas interact, first let's talk about optical photons, and I'm not an optics expert, but if you think about the way that that lenses work, it has to do with the change in index of refraction from one side, from over that optical boundary, so from air to glass, let's say. And the change in index of refraction leads to some sort of interference effects that that changes the direction of a ray of light as it crosses that boundary. That's Snell's law. That interference relies on kind of a large number of interactions, that photon sees, in some sense, the material that it's traveling through in a very different way from how gammas interact. So when you get up to gamma energies, as you know, they're primarily just flying through empty space. Gammas mostly see empty space, and then once in a while they'll undergo a large kind of collision, an interaction, an elastic scatter, or an inelastic interaction of some kind, and those tend to be large energy transfer. So a gamma will primarily travel through material until it interacts, and then it will undergo some scatter, which could be large angle or small angle. But that's very different physics from the kind of collective interaction with the material that the optical photons experience. So hopefully that made sense. I mean, the way that's the way I think about it, is just kind of the experience of a gamma or a neutron as it travels through a material is it's mostly just flying through empty space, and then occasionally it interacts with some piece of that material in a more catastrophic way.
All right, great. Thank you very much. Yeah, if there are any other questions, I guess if you want to stay online for one more minute, that would work. If not, thank you everyone for joining the presentation.
Yep, thanks to all of you. And I will stay on in case there's any other questions, but take care and have a great almost weekend.